Okay, welcome back. Pages 13 and 14 of the sequences in series packet. This is actually just 3 problems, so let's do it. The first one is a kind of just a little math problem. Take the 3 terms, a squared, b squared, c squared, and suppose that they're in arithmetic progression. That's just a kind of an old-fashioned term, arithmetic progression, just to say that, you know, these are 3 terms of an arithmetic sequence. And if that's true, show that b plus c, c plus a plus b, that those 3 terms are in a harmonic progression. Okay, so you need to know what a harmonic sequence is. A harmonic sequence is a sequence in which the reciprocals are arithmetic. So, what do I need to prove? I basically need to, so this is the theorem, and so if we're doing this kind of carefully, then I should assume that a squared, I'll just say a squared, b squared, c squared is arithmetic. And by the way, what does that even mean? That a squared, b squared, c squared is arithmetic? Well, it just means that the gap between b squared and a squared is the same as the gap between c squared and b squared. So this is just the definition of what it means to be arithmetic. That b squared minus a squared equals c squared minus b squared. Okay, so from that, somehow, I need to show that this sequence is harmonic. So I need to show that b plus c, c plus a plus b is harmonic. And okay, as often happens in this unit, it's not obvious at all how to proceed in the sort of forward direction. So when you're trying to do a proof, you very often just kind of work backwards and you figure out, okay, well, what does it mean to show that these 3 terms are in a harmonic progression? Well, I can tell you exactly what that means. 3 numbers are in a harmonic progression if their reciprocals are in an arithmetic progression. Okay, so instead, what I will do is I will show that 1 over b plus c, comma, 1 over c plus a, comma, 1 over a plus b is arithmetic. So in other words, it suffices to show this. If I can show this, then therefore this is true. Okay, well, what does it mean for this to be arithmetic? Well, for this to be arithmetic, it means that the gap between this term and this term is the same as the gap between this term and this term. And so what I really need to show is that 1 over c plus a minus 1 over b plus c is equal to 1 over a plus b minus 1 over c plus a. So in other words, show that the gap between these 2 is equal to the gap between these 2. Okay, well, is this true? I have no idea. But this can be simplified, of course. So let's do that. Let's just kind of get a common denominator here. So I will multiply by b plus c over b plus c. Here I'll multiply by c plus a over c plus a. I'm getting a common denominator on the left. This is really just kind of some algebra 1 type stuff. I'm getting a common denominator on the right as well. Here I multiply, yeah. Okay, and okay, what do I end up with? I end up with b plus c minus c plus a over a plus, well, I'll just write it out the way it's written. B plus c times c plus a equals c plus a minus a plus b. Maybe I'll do it like that. All over a plus b, c plus a. In other words, in order to show that this is harmonic, I need to show that this is arithmetic. And to show that this is arithmetic, all I have to do is demonstrate that the gaps are the same. Well, what are these gaps? I'm now just doing the algebra. And, okay, well, first of all, I need to, so I basically, maybe I should write that again. what I need to do is I need to show that this is true. Of course, I can just now cancel C plus A from both sides, or rather multiply through by C plus A. What do we get? Simplifying this top here a little bit, the minus C cancels, and I get B minus A over B plus C is C plus B over A plus B. Okay, so all I have to do is show that this is true now. Is this true? Well, let's just cross multiply. And if I cross multiply, I get B minus A times B plus A is B squared minus A squared. And B plus C, sorry, that should be minus B there. B plus C, or rather C plus B times C minus B is C squared minus B squared. Oh, that looks familiar. That is just true. Whoa. This is just true because A squared, B squared, C squared is arithmetic. And that's basically the whole problem, right? And now, if you want to be a very kind of good person, then you should just, explain why I don't need to rewrite this whole thing again. Because, well, now follow the logic. Read this proof from the bottom up. I know that A squared, B squared, C squared is arithmetic. That was my assumption. So, does it follow, therefore, that B squared minus A equals C squared minus C squared, B squared minus A squared equals C squared minus B squared? Yes, that's just the definition of what this means to be arithmetic. Well then, just do some algebra, to convert between these two lines. I guess, what am I really doing? I'm sort of, well, I'm dividing by A plus B on both sides, and I'm dividing by B plus C on both sides, I guess, is what's really happening. And here I'm then multiplying through by A plus C. So okay, what I'm trying to say is that in doing this proof backwards, I actually just did the proof, because every one of these steps of mine is totally reversible. And you can just confirm that to yourself. And so I've showed, actually, if you just rewrite this, if you really want to rewrite it, you can. I'm not going to right now. But you can rewrite this proof going from this line to 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 this line. And if this sequence is arithmetic, then by definition this sequence is harmonic, and we're just done. Okay, hopefully that was good. All right, that was number 43. Let's do 44. All right. This number 44, I think, is just like a good old-fashioned just math problem. Just sequences and patterns and do it. So what do we got here? The first term of a geometric sequence is 27. So the first term is 27. And the nth term is 32 over 9. So the first term is 27. The nth term is 32 ninths. Okay, and this is geometric. And okay, great. Also, the sum of the first n terms is 665 over 9. Goal, find n and r. Okay, find n and r. Alright, and I want to do this in kind of a principled way, which is to say, not just with sort of guess and check or just kind of feeling it or whatever. So do this kind of systematically, such that this would work regardless of the numbers. Okay, well, there's just a lot I don't know right now. I have this first term, 27, and then I have, kind of subsequent terms of this sequence, but I don't know. I know it's geometric, but I don't know what r is. All I know is that when I multiply by r a whole bunch of times, I eventually get 32 ninths. And okay, maybe that's kind of the first place to start. So here, put a kind of a box around this because that's just a statement of the problem. I know how to write the nth term of a geometric sequence, the nth term is just going to be, the first term times r n minus 1 times. In other words, for this particular sequence, 32/9 is what I get when I start with my first term, 27, and multiply by r n minus 1 times. Okay, so this is an interesting little formula, but unfortunately it's in two different variables. There's an r and an n here, because I still don't know how many times I have to multiply by r to get 32/9, and I also don't know what r is. Okay, well that's when I reach for this second fact here, that the sum of the first n terms is 665 over 9. Well, what is the formula for the sum of the first n terms of a geometric sequence? It's going to be a times 1 minus r to the n over 1 minus r. And so in this case, I get that 665 over 9 is the first term, which is 27, times 1 minus r to the n all over 1 minus r. Alright, and now, this entire problem now has just been boiled down to, can you solve this system of two equations in two variables? This equation has r's and n's in it. This equation has r's and n's in it, but I should be able to kind of just make this work. Alright, and there are lots of different things you might do right now. Some are good ideas, some are bad ideas. If you're algebraically experienced, then I think the simplest thing to do is to get this r to the n out of my face. In other words, let me multiply both sides of this equation by r. Let me multiply by 9 first. So I get that 32 equals 27 times 9 is 243 r to the n minus 1. Well, man, I really, really wish that that were r to the n instead of r to the n minus 1. So I just multiply by r. So 32r is 243 r to the n. Yeah. And looking good. Just trying to maybe do even something cooler. But maybe I don't want to do anything cooler. Yeah, maybe I don't want to multiply by 9, because that just kind of sends me round and round in circles. Backtrack 1 minute. Just multiply through by r, and you just get 32r over 9 equals 27 r to the n. Did I do that right? Yeah. Why is that better? Because this is 27r to the n right here. Or, yeah, I don't know exactly what the simplest thing to do here. Maybe I'll even maybe it's even just easier to just divide by 27. So kind of the opposite of what I was saying before. So what do you get? You get 32r over 243. Sure. Okay, so what's this? This is just a mild modification of this formula here in the box. But now you see that you can just take this and sub it directly in here. Okay, so maybe this problem is not so hard. What do we get? 665 over 9 equals 27 times 1 minus, and in place of r to the n, I write 32r over 243. Yeah, cha, all over 1 minus r. Okay, and now we're back at the level of just algebra 1. This is a little bit annoying, but this is now a single equation in a single variable. Okay, let's go. Let's cross, well, maybe, what should we do? Let's just cross multiply to get rid of fractions. So 665 times 1 minus r. And here if I multiply by 9 I get 243. So that's 243 times 1 minus 32r over 243. 81, 243, Jean, sure. And yeah. So what's this on the right hand side? When I multiply through I get 243 minus, the 243's cancel. So So 32r. Over here I get 665 minus 665r. So this is in fact just a linear equation even. And well, what do we get? Add 665 to both sides, and I'm going to get 6 something, 41? No, what happened? 631? Wait a second. Jeez. 633. Yeah. R over, this kind of strikes me as being wrong. Anyway, when I subtract 243 from this side, I get 2, 2, 4. So I get 4, 2, 2. So is this something nice? What is R? It's 422 over 633. And I guess that's just 2/3. Is that just 2/3? Yeah, it's totally just 2/3. I'm multiplying by 211 over 211. 630, yep. Okay, therefore, I have just concluded that R is just 2/3. And once I know that R is 2/3, let's see, what's the simplest thing to do next? Well, I guess I go maybe here now, and to figure out what n is, what's the best way? Who knows? R is 2/3. What's n? I guess I just go back to somewhere. Maybe just here, say. Okay, so now if I know that R is 2/3, so I get 32 over 243 times R is 2/3, so I've multiplied by 2/3. That's going to be 2/3 to the n. And let's see, does this simplify? I hope it does. This is going to be 32 times 2 is 2 to the 6th, and 243 is also is 3 to the 6th, and therefore n is 6. So I call that not guess and check. Okay, is that all we have to find for this problem? Yeah, find n and r. So yep, so as it turns out, the common ratio is 2/3, and you need to multiply by r a bunch of times, and by the time you get to the 6th term of this sequence, the value is 32/9, and the sum of the first 6 terms is 665 over 9. Okay, one more problem, which I think is kind of interesting. So next page. Page 14. Page 14. I'm determined to make this video be less than, yeah, it's going to happen. Okay, so here is I'll just read it aloud. Here is a famous, this is problem number 45. Here is a famous problem posed in the 13th century by Leonardo da Pisa, better known as Fibonacci, big hint. Suppose we have one pair of newborn rabbits of both genders. We assume that the following conditions are true. 1. It takes a newborn rabbit 1 month to become an adult. Okay. A pair of adult rabbits of both genders will produce one pair of newborn rabbits of both genders each month, beginning 1 month after becoming adults. So that's kind of crazy. That means if you're a rabbit, this is just built into the assumption of the problem. It's probably not true for rabbits, but this might be true for mice? I don't know. Some of these mammals have extremely short childhoods. You know, they're born and then 3 months later they're already kind of reproducing. I don't know exactly what the numbers are for rabbits or mice. Really, I don't really know anything. But anyway, the built into the assumption of this problem is that rabbits are born. 1 month after being born, they have already reached full sexual maturity and are doing rabbit things, and now 1 month later, new babies will be born. Okay, and also the rabbits do not die. So okay, this is kind of an interesting problem because it's not quite a geometric increase. there are sort of more and more and more rabbits, but the old rabbits are also already there. And there's also this kind of like delay, right? Because the rabbits are born and it's not like the very next month they produce offspring. There's sort of 1 month that goes by where they're growing, and then the following month they produce offspring. Okay, so how many rabbits will there be after 1 year? Write a recursive equation for r sub n. The number of pairs of rabbits n months from now expressed in terms of blah 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 blah. Okay, so yeah, so we start with 1 pair of newborn rabbits. So let r sub n be the number of pairs. So this is the number of pairs of rabbits n after n months, just after n months. So start the clock now at time 0, and I say that now at time 0, r sub 0 is 1. Why is that? Because there are currently, at the very beginning of this problem, a pair of newborn rabbits. Okay, so to keep track of which rabbits are adults and which rabbits are babies, I will draw the babies tiny and the adults big. Okay, so here's kind of the situation. We just have to play around and draw pictures and sort of just get it. So at the beginning of this problem, we have a pair of newborn rabbits. So I'm going to draw these 2 tiny baby rabbits, just born. Okay, well now let's check in on these rabbits 1 month later. What has happened to these rabbits 1 month later? Well, they've now grown up, and they are now adult rabbits, and they are ready to start reproducing. But I still have just 1 pair of rabbits. I'm counting the pairs. Okay, well now, what? After 2 months, how many rabbits do I have? Well, I have my old 2 rabbits, but now those original 2 rabbits are adults, and they have now produced a pair of babies. Okay, so there must be 2 pairs of rabbits then, after 2 months. Okay, how about after 3 months? Okay, well now we have to kind of be a little bit careful, because what do we have? Well, we have the original rabbits. They're still just sitting there. But also, they have produced babies. Cha-cha, cha-cha. And also, the babies have now grown up. So I think the answer is 3. Okay, how about after 4 months? Alright, well, let's track every single pair of rabbits from the previous month. This is recursive after all, and see how many rabbits we should expect for the next month. Well, first of all, the rabbits never die, so these 2 rabbits are still there. So I'm going to draw them in. Boom, boom, and boom, boom. But also, in addition to not dying, they produce new babies. And how many babies? Well, they each produce a pair of babies, these adults. So choop choop and choop choop. And also, those ones that were babies in the previous step have now gotten bigger and have grown up and have become adults as well. Okay, so the answer is that there are 5. Alright, don't stop now. How many after 5 months? Well, once again, I have all of my adults are still adults. Cha-cha, cha-cha. Each of those adults have produced babies, and the babies have grown up. So I shift these babies up to like the adult column. I think this is the good way of doing it. And now the 3 adults have all made babies. And so the answer is 8. Oh, I think I see where this is going. Okay, 1 more, and then we're going to call it like we get it. What does it say to do? Well, whatever. This is good enough. Okay, how about after 6 months? Well, once again, all 5 adults from the previous month are still there. But then also, the 5 adults have all made babies. So, but also the 3 babies from the previous generation have all grown up and are all adults now. Okay, what is going on here? And so what's the answer? The answer is 13. Alright, I think you are suspecting that the answer to this problem is that the number of rabbits each month is the Fibonacci sequence. This is the origin of the Fibonacci sequence. This is why it's called the Fibonacci sequence. It's named after this guy, Fibonacci, and this is the math problem that he posed and solved. And the Fibonacci sequence is really important. It comes up all the time in all kinds of different situations. So, right, what is going on? Besides just observing that these numbers are 1, 1, 2, 3, 5, 8, 13, which is all you had to do, let's try to understand this and to prove that this is going to, in fact, continue. Okay, so I'm not going to give like a rigorous proof. I'm just going to sort of kind of explain what's happening. So let's take it maybe from here. Okay, how do you get from this sort of R4 to R5? Well, let's see. There are kind of 3 sort of categories. There is this category of rabbit, which I will draw in red. What is happening to this category of rabbit? It's just being sent directly here. Chop, chop, chop. Then there is this category of rabbit, which is being sent here. In other words, just as I explained at the time, you have the adults in one generation become are still adults in the next generation, but whoever are the babies in one generation become also adults in the next generation. In other words, the best way to put this perhaps is that the total number of adults after 5 months is the sum of the total number of adults in the previous month and the number of babies in the previous month. In other words, whatever the total number of rabbits are at a certain stage, let's just call this stage 4. I mean, that's what it is, right? After 4 months. Here I am in stage 4. The total number of rabbits in stage 4, which consists of adult rabbits and baby rabbits, becomes the number of adult rabbits in the next step. Because how many adults do I have in stage 5? I have the adults that I had plus the kids are now adults. Okay, but I also have some kids. Where do these kids come from? The new baby rabbit comes specifically from the adults in the previous step. Okay, so what is this really saying? What this is really saying is that adults in the adults in stage 4 are still adults in stage 4. The babies in stage 4 become adults in stage 5. Sorry, the adults in stage 4 are still adults in stage 5. The babies in stage 4 become adults in stage 5. But the number of babies in stage 5 is the number of adults in stage 4. But what is the number of adults in stage 4 really? The number of adults in stage 4 is just the number of total rabbits in stage 3. So in any given stage, the total number of rabbits in that stage, adults and babies, become the number of adults in the next stage. And in the following stage, the number of adults is the number of rabbits in the previous stage, plus the number of babies produced by the adults in the previous stage, which is the rabbits in the previous stage. Okay, therefore, another way of putting this is, if I want to count the total number of rabbits there are at stage 5, I want to think of it in terms of 2 categories, the number of adults and the number of babies. How many adults do I have in stage 5? Answer, it's just the number of rabbits in stage 4, as I've already said now like 4 times. And how many babies do I have in stage 5? The number of babies I have in stage 5 is equal to the number of adults I have in stage 4, and the number of adults I have in stage 4 is just the number of total rabbits in stage 3. And there is the recursive rule. More generally, maybe we just do kind of like one more or something, right? What about R6? How many total rabbits do I have in the after 6 months? Answer, I have adults plus children. How many adult rabbits do I have? Well, I have 8 adult rabbits. Why do I have 8 adult rabbits? Because I had 8 rabbits in the previous generation, 5 of which were adults, 3 of which were babies, but the babies all grew up. Therefore, the number of rabbits I have after 6 months is the number of adults I had, is the number of adults plus the number of babies. And the number of adults is just the number of rabbits in the previous generation. And the number of babies in the 6th generation is the number of adults in the 5th generation, which is just the number of rabbits in the 4th generation. And in general, the number of rabbits in any particular generation after n months is going to be the number of adults rabbits, which is the number of rabbits in the previous month, total rabbits in the previous month, plus the number of new babies, and the number of babies is the number of adults in the previous round, which is the number of rabbits in the previous round. Alright, that was an extremely thorough explanation of that. And I guess if you continue out this for 12 months, you get that there are 466 rabbits there will be after 12 months. Okay, goodbye.